Dear students, in this session we can discuss about some problems related with elasticity. The first one, a metal wire of length 5 meter and a diameter 2 millimeter is stretched by hanging a mass of 8 kilogram at one end and keeping the other end fixed to a ceiling. Find the extension produced if the Young's modulus of the material of the wire is capital Y is equal to 7 into 10 raised to 10 Newton per meter square. Here we have a steel wire which is fixed at one end, and at the other end a load is attached, and we are asked to find the extension produced. So let us write first the data given in the problem. Here we have given the metal wire of length 5 meter. So the original length L is equal to 5 meter. So L is equal to 5 meter, and the diameter is given. So small d is equal to 2 millimeter. From that we can write the radius R is equal to 1 millimeter. So let us convert into meter. That is 1 into 10 raised to negative 3 meter. And here the load is attached. So the mass M is equal to 8 kilogram. And we are also given the Young's modulus, that is Y is equal to 7 into 10 raised to 10 Newton per meter square. So let us write the expression for Young's modulus, that is Y is equal to F L divided by delta A into delta A, or delta L into A. So let us expand. Here the load is attached. That means here F is equal to M into G. So M into G by L divided by, since there we have the wire, so the area cross section, that is pi r square into the extension delta L. Therefore, delta L is equal to mgl divided by pi r square into y. So let us substitute all these values here. M is equal to 8 kilogram into 9.8. That gives the force, the stress, the applied force, not the stress. Then original length is 5 meter, all divided by pi, that is 3.14, and radius is 10 raised to negative 3. So that is square, and here we have the 10 raised to plus 10. So here the power become 10 raised to plus 4. So after the calculation, you will have the delta L. 1 is 1.7878 into 10 raised to negative 3 meter. The next one. A hydraulic press contains 0.5 meter cube of oil. Find the decrease in the volume of the oil when it is subjected to a pressure of 2.6 into 10 raised to 7 Pascal. The bulk modulus of the oil is B is equal to 5 into 10 raised to 9 Pascal. Here we are asked to find the decrease in volume, the change in volume. So let us write the expression for bulk modulus. That is B is equal to negative PV divided by delta V. Since we are asked to find the decrease in volume, delta V is equal to negative PV divided by B. Now let us write the information given in the problem. Here already the initial volume capital V is equal to 0.5 meter cube, and the applied pressure capital P is equal to 2.6 into 10 raised to 7 Pascal, and the bulk modulus is given, that is 5 into 10 raised to 9 Pascal. So let us substitute all these values in the given equation. So the delta V is equal to negative 2.6 into 10 raised to 7 original volume, initial volume, that is 0.5, all divided by the value of B is equal to 5 into 10 raised to 9. So after the calculation, you will get the value of the change in volume is equal to negative 2.6 into 10 raised to negative 3 meter cube. So the negative value of delta V implies that here as the pressure applied, as the pressure increases, there is a decrease in volume. The next one, a solid brass sphere is initially surrounded by air, and the air pressure exerted on it is 1.5 into 10 raised to 5 Newton per meter square. That is a normal atmospheric pressure. The sphere is lowered into the ocean to a depth where the pressure is 2.8 into 10 raised to 7 Newton per meter square. The volume of the sphere in the air is 0.85 meter cube. By how much does this volume change once the sphere is submerged? The bulk modulus of the brass is 6.1 into 10 raised to 10 Newton per meter square. I think you can read it once more. I hope all of you have understood. Here we are asked to find the change in volume of the sphere when it is submerged. Here we have given the initial volume, that is when the sphere is outside the water, that is 0.85 meter cube. When it is under, there is a normal pressure, that is 1.5 into 10 raised to 5 Newton per meter square. Okay. When it is submerged, when it is immersed in the ocean, the additional pressure is, that is the pressure due to the depth, is 2.8 into 10 raised to 7 Newton per meter square. So here we should understood that the increase in pressure to cause for the change in volume is 2.8 into 10 raised to 7 Newton per meter square. Am I right? No. Because Here we are given it is the total pressure when the sphere is at at a given depth. So this total pressure includes the air pressure at the top of the water. So the amount of the pressure that caused a change in volume is is only due to the pressure that is caused by the depth of the volume, the depth of the water column. So for that we have to decrease the value of the normal pressure from the total pressure 2.8 into 10 raised to 7 Newton per meter square. So let us let us write the information already given in the problem. So the air pressure on the brass sphere, the air pressure on the brass sphere is equal to 1.5 into 10 raised to 5 Newton per meter square. The pressure at the depth of the ocean. The pressure at the depth of ocean is equal to 2.8 into 10 raised to 7 Newton per meter square. So the pressure on the brass sphere on the brass sphere when it is submerged. When it is submerged, that is equal to 2.8 into 10 raised to 7 minus 1.5 into 10 raised to 5. And the initial volume of sphere, that is P is equal to 0.85 meter cube. Bulk modulus of brass, bulk modulus B is equal to 6.1 into 10 raised to 10 Newton per meter square. So let us write the expression for bulk modulus, that is B is equal to negative PV divided by delta V. Therefore, delta V is equal to negative PV divided by B. So let us substitute delta V is equal to negative. What is the value of P? P is equal to 2.8 into 10 raised to 7 minus 1.5 1.5 into 10 raised to 5. So that is the pressure into the change into the initial volume, that is 0.85, all divided by the value of the bulk modulus, 6.1 into 10 raised to 10. First you have to make the subtraction and do the rest of the calculation. You will get the value of the change in volume is equal to 3.88 into 10 raised to negative 4 meter cube. Now the next problem. A square copper slab having a side of 75 centimeter and a thickness of 15 centimeter is subjected to a shearing force of 12 into 10 raised to 4 Newton on the thickness Y side. The lower edge is kept fixed to the floor. How much will the upper edge be displaced or sheared? The rigidity modulus of the copper is 4.2 into 10 raised to 10 Newton per meter square. You have to read it once again. A square copper slab having a side of 75 centimeter and a thickness 15 centimeter is subjected to a shearing force of 12 into 10 raised to 4 Newton on the thickness Y side. The lower edge is kept fixed to the floor. How much will the upper edge be displaced or sheared? The rigidity modulus of the copper is 4.2 into 10 raised to 10 Newton per meter square. Here, a square copper slab is taken, and it has a one side is 75 centimeter, and the thickness of the slab is 15 centimeter, and there is a force is applied, a shearing force is applied, and on the thickness Y side. As a result, the top surface, the top edge is sheared. Okay, so we are asked to find how much will the top edge is displaced. How can we do this problem? Here, a shearing force is applied parallel to the thickness wise face. So, the area on which the force is applied, that can be calculated by, that is A is equal to 75 into 15 centimeter square, that is equal to 1125 centimeter square. Let us convert into meter square, that is 0.1125 meter square. And we know the shearing stress. The shearing stress equal to shearing force per area. Here the force is equal to 12 into 10 raised to 4 Newton divided by the area is equal to 0.1125. So after the calculation you will get 1.067 into 10 raised to 6 Newton per meter square. X by H is equal to, what do we know what is shearing strain? Let us give the values. Shearing stress divided by the shearing strain is equal to, so that is shearing stress. We know the expression, that is X by H 0 X by 67 into, and the rigidity modulus is 6 divided by the rigidity modulus is equal to 4. Shearing stress by 2 shearing strain into 10 raised to 10. Now therefore the value of x, that is the amount of shearing, that can be calculated as x equal to h into this value, that is 1.067. Therefore into shearing strain is equal to all divided by 4.2 into 10 raised to, that is, so let us write again h. Here the h is 75 centimeter, so let us convert into 0.75 or 75 into 10 raised to negative 2 into 1.067 into 10 raised to 6 all divided by 4.2 into 10 raised to 10. So after the proper calculation, you will find the value of x, the amount of shearing or the distance through which the upper edge is sheared or upper edge is displaced is given as can be found as 1.9 into 10 raised to negative 5 meter. So this is the amount of shearing. The next one, in a circus performance, an actor tries to swing in a cable made of steel. Now suppose the tension in the cable is 940 Newton as the actor reaches the lowest point. What diameter should a 10-meter long steel cable have if we do not want it to stretch more than 0.5 centimeter under these conditions? The Young's modulus of steel is 20 into 10 raised to 10 Newton per meter square. So here a circus performer is swinging on a steel cable, and when he reaches his lowest position, the load on the force acting on that cable is 940 Newton, and the expected and the maximum expected elongation is 0.5 centimeter for the cable. So for that, what should be the diameter? What should be the diameter? So that we can use the formula, with the expression for the Young's modulus. So let us write the force acting on the load acting on the cable is 940 Newton, and the original length, the initial length is of the steel cable is 10 meter, and the maximum change in length, the maximum extension is 0.5 centimeter, that we can convert into meter, that is 5 into 0.5 into 10 raised to negative 2, that is 5 into 10 raised to negative 3 meter, and the Young's modulus y is given 20 into 10 raised to 10 Newton per meter square. So let us first write, we are asked to find the diameter. So for that we have to find the area of cross section. From that we can find the diameter. Okay. So let us first write the expression for y. Y is equal to FL divided by A delta L. So from that A is equal to FL divided by Y into delta L. Okay. So let us substitute. If we have the value 940 and the L it is 10 meter, and Y 20 to 10 raised to 10, and the maximum change in length is 5 into 10 raised to negative 3. So after the calculation, you will find the area of cross section should be 9.4 into 10 raised to 6 meter square. But we know the area of cross section is A is equal to pi r square, or we can write pi d by 2 square, that is pi d square by 4. So from that, d square equal to 4 into A divided by pi. Therefore, d is equal to square root of 4 into A divided by pi. So let us substitute all these values here. 4 into the area cross section has the value 9.4 into 10 raised to negative 6, all divided by the value of pi, that is 3.14. So you can complete the calculation and you will find the the diameter of the cable should be 3.46 into 10 raised to negative 3 meter. So this is the required diameter for the steel cable. Next one, a 200 kilogram load is hung on a wire of length 4 meter. Cross sectional area 0.2 into 10 raised to negative 4 meter square, and Young's modulus is 8 into 10 raised to 10 Newton per meter square. What is the increase in the length? What is the increase in the length? So it is a very straightforward question. So let us first write the information given here. The load, the mass attached is M is equal to 200 kilogram, and the original length is equal to 4 meter, and the area cross section A is equal to 0.2 into 10 raised to negative 4 meter square, and Y is equal to 8 into 10 raised to 10 Newton per meter square. So let us first write Y is equal to, here we are using mg instead of F. Here the mass is attached. So mgl divided by A into delta L. So therefore delta L is equal to mgl all divided by Y into A. So let us substitute all the values. Here 200, m is 200, that is into 9.8. Length is equal to 4 meter. Length is equal to 4 meter divided by Young's modulus 8 into 10 raised to 10, and area cross section is 0.2 into 10 raised to negative 4. So after the calculation, you can have the change in length is equal to 4.9 into 10 raised to negative 3 meter. Okay, the next one. Here we are asked to find the diameter of the second steel wire to support the tension of 25 kilonewton with the same extension. So, let us write the expression for y. Y is equal to F L divided by A delta L, that we can F L by R square into delta L, that I can again, that is F L divided by pi d by 2 whole square into delta L, that is equal to F L divided by pi d square by 4. This 4 will come to the numerator. So 4 FL pi d square into delta L. So for the first cable, let us write Y1 is equal to 4 F1 L1 divided by pi d1 square into delta L1. For the second cable, let us write Y2 is equal to 4 F2 L2 divided by pi d2 square into delta L2. Since here Y1 equal to Y2 and also L1 and L2 are the same, and the expected change in length in both cables are the same. So delta L1 is equal to delta L2. So let us substitute. So we can equate 4 F1 L1 divided by pi d1 square delta L1 equal to 4 F2 L2 divided by pi d2 square delta L2. So these 4 can be cancelled. L1 and L2 can be cancelled. Pi can be cancelled out. Delta L1 and L2 can be cancelled. Therefore, d2 square is equal to F2 into d1 square divided by F1. Okay. So let us substitute. So therefore d2 is equal to square root of F2 d1 square divided by F1. So let us substitute. F2 is equal to 25 kilonewton. So 25 into 10 raised to 3 d1 1 millimeter. So 1 millimeter we know 10 raised to negative 3. So negative 3 whole square, and divided by F1 is equal to 0.5 in kilonewton, that is into 10 raised to 3. So after the calculation, you will get the diameter should be 7.07 into 10 raised to negative 3 meter. So that is equal to 7.07 millimeter. Okay, this should be the diameter of the second steel cable. And also the next one, 250 liter oil of compressibility K, that is equal to 20 into 10 raised to negative 6 per atmosphere, is subjected to a hydraulic press. Find the increase in the volume of the oil when it is subjected to a pressure of 1.6 into 10 raised to 7 Pascal. Here we are given the compressibility and we are asked to find the decrease in the volume of the oil when it is subjected to a pressure of 1.6 into 10 raised to 7 Pascal. First, the original volume. The initial volume V is equal to 250 liter. So that we have to convert into meter cube. So what is the relation? 1 liter is equal to 10 raised to 3 meter cube. We have to remember the relation, that is 1 liter is equal to 10 raised to negative 3 meter cube. Okay. So 250 liter is equal to 250 into 10 raised to negative 3 meter cube. Okay. And we are given the compressibility. So the compressibility and the bulk modulus is related by B is equal to 1 by K. B is equal to 1 by K. Okay. So here it is also we are given, it is in atmospheric pressure. So that also we should convert. That is 1 by K, that is 1 by 20 into 10 raised to negative 6 atmosphere, that is equal to, what is the value of 1 by 20? 1 by 20 is equal to 0.05 into 10 raised to plus 6, that is equal to 5 into 10 raised to 4, that is that much atmospheric pressure. But we know when it is converted into Pascal, we should convert it into Pascal. So what is the value of the 1 Pascal is equal to 1 atmospheric is equal to 1 atmosphere is equal to 1.013 into 10 raised to 5 Pascal. So that is equal to 5 into 10 raised to 4 into 1.013 into 10 raised to 5 Pascal. So Pascal is the SI unit. Okay, so that is the value of the B. And the pressure applied is equal to 1.6 into 10 raised to 7 Pascal. Therefore, let us write first B is equal to negative PV divided by delta V, or delta V is equal to negative PV divided by B. So let us substitute here. B is equal negative P is equal to P 1.6 into 10 raised to 7 Pascal, and volume, that is we have converted, that is 250 into 10 raised to negative 3, and the value of B is equal to 5 into 10 raised to 4 into 1.013 into 10 raised to 5. So after proper arranging the powers of 10 and calculation, you will find that the change in volume is equal to 0.82 meter cube. That is the change in volume. Here the negative sign implies that the volume is decreased. So the next problem is, how much load is needed to elongate a steel wire to 0.5% of its original length? The diameter of the wire is 2 mm and Young's modulus of the material of the wire is 20 into 10 raised to 10 Newton meter square. Okay, here we are asked to find the value of the load needed for a particular elongation. So here the elongation is not directly given, but it is given as the percentage of the original length. That is, delta L is equal to L into, that is original length, into 0.5 percentage. That is 0.005 L. Therefore, delta L by L is equal to 0.005. And the diameter is given. The diameter is D is equal to 2 millimeter. From that, radius is equal to 1 millimeter. Convert into meter, radius equal to 10 raised to negative 3 meter. And the value of y, that is 20 into 10 raised to 10 Newton per meter square. And the value of g, that is 9.8 meter per second square. So let us write the expression for Young's modulus y is equal to FL divided by, here we have the steel wire, so that is equal to pi r square into delta L. So from that, F equal to, that is mg equal to y into pi r square into delta L by L. Therefore, m is equal to y into pi r square into delta L by L divided by g. So let us substitute. Here y is equal to 20 into y is equal to 20 into 10 raised to 10. So let us write 20 into 10 raised to 10 pi 3.14, radius point, that is 10 raised to negative 3 whole square. Delta L by L is equal to 0.005 whole divided by 9.8. So after the calculation, you will find the value of the load needed for the particular elongation is 320.4 kilogram. Okay, now the next problem. A wire of length 2 meter is subjected to a longitudinal stress by fixing the one end and hanging 500 kg mass at the other end. If the wire stretched for 5 mm and its Young's modulus is 9.1 into 10 raised to 10 Newton per meter square. Calculate the radius of the wire. So let us write the information given, that is y is equal to 9.1 into 10 raised to 10 Newton per meter square. Original length L is equal to 2 meter and delta L is equal to 5 millimeter, that is equal to 5 into 10 raised to negative 3 meter, and the hanging mass M is equal to 500 kilogram. So there we are asked to find the radius of the wire. So let us write the expression for y, that is y is equal to FL divided by A delta L, that is equal to F is equal to mgl divided by pi r square into delta L. From that we can write the expression for radius. That is, first we have to write the radius square, that is equal to mgl divided by pi y delta L. Therefore, radius r is equal to square root of mgl divided by pi y delta L. So let us substitute all these values and complete the calculation. So let us write m is equal to 500, g is equal to 9.8, L is equal to 2 meter, all divided by pi has the value 3.14, y, that is equal to 9.1 into 10 raised to 10, delta L is equal to 5 into 10 raised to negative 3. So after the calculation, you will get the value of the radius of the wire is equal to 2.62 into 10 raised to negative 3 meter, that is equal to 2.62 millimeter. The next one, a copper rod of cross-sectional area 0.5 centimeter square and length 1 meter is elongated by 2 into 10 raised to negative 2 millimeter, and a steel rod of the same cross-sectional area but 0.1 meter in the length is elongated by 1.5 into 10 raised to negative 3 millimeter. Which rod undergoes greater tensile strain? Here we have the two wires. One is made of copper and another is the steel rod. Both have the same cross-sectional area, but their elongation is different. So we are asked to find which rod undergoes the greater tensile strain. We know the expression for tensile strain. The tensile strain is equal to the change in length divided by original length. So delta L divided by L. So for copper, For copper, the strain is equal to delta L by L. So for copper, delta L is equal to 2 into 10 raised to negative 2 millimeter. So let us, when we convert into meter into 10 raised to negative 3, that is, in total we have the into 10 raised to negative 5 meter, divided by the original length. For the copper rod it is 1 meter. So the elongation, so the strain is, in the case of copper, is 10 raised to negative 5. For the steel rod, which has the same cross-section area as that of the copper, the strain is equal to delta L by L, that is equal to, here the elongation is 1.5 into 10 raised to negative 3. When it is converted into meter into 10 raised to 1 more into 10 raised to negative 3, that is, in total is 10 raised to negative 6, will divide by the original length, that is 0.1. So that is equal to, here a 0.1 means into 10 raised to negative 1. So 1 here 10 raised to negative 6. So 1 10 raised to negative 1 can be cancelled out. So the strain is equal to 1.5 into 10 raised to negative 5. So from these two values, we can conclude that the copper rod undergoes, because it has the largest strain. So the copper rod undergoes greater strain, the greater tensile strain.